Hi students, here we have the another video for the fast track revision series for JEE Main. In this we are going to study about the Coulomb's law. According to Coulomb's law, when 2-point charges say Q1 and Q2 are placed at some distance r apart in vacuum, then they will attract or repel each other with a force which is proportional to square of the distance between proportional to product of the charges and inversely proportional to the square of the distance between them. When we combine these two equations, we are having F is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. Now here this 1 upon 4 pi epsilon naught is the proportionality constant whose value will be nine into 10 power 9 Coulomb Newton meter square per Coulomb square. In SI unit 9 into 10 to the power 9. And this epsilon naught is known as the permittivity of free space. Free space means here vacuum, and its value will be in SI unit 8.85 into 10 power minus 12. This is the value of epsilon naught. Now if some medium will be filled in between them, then we'll see what is going to happen later on. And the force exerted by Q1 on Q2 or Q2 on Q1 is going to be equal and opposite. You have to remember the force is a vector quantity. So it is only going to tell us that what is the force between two charges. If it is like charges, they will repel each other. If it is unlike charges, they will attract each other. That concept we have to use. Now the same law in vector form also we are writing. Consider 2-point charges Q1 and Q2 placed here, Q1 and Q2, and they are placed at the position vectors R1 and R2. Then force experienced by 1 due to 2. Always remember, in vector form, charges has to be substituted with sign. This is the core concept you have to remember. Now let us say we have defined the R vector from A to B. This is O, this is A, this is B. AB vector is equal to OB vector minus OA vector, and we can write it as R2 minus R1. This vector we have defined as R vector. Now we are writing the force experienced by 1 due to 2. Force experienced by Q1 due to Q2. And force experienced by Q2 due to Q1. They will be equal and opposite. Now, force experienced by 1 due to 2 will be along minus R cap vector. Along minus R vector this way. Right? So you have to be careful in the directions here. The equation comes force experienced by 1 due to 2, 1 upon 4 pi epsilon naught Q1 Q2 upon mod R square, and the direction is in vector form if you are writing along minus R vector. Now along why minus R vector? Because if say both these charges are attractive in nature, if these charges are positive, then force will be in this direction. If both are negative, force will be in this direction. If they are of opposite sign, force will be in this direction. If Q1, Q2 both positive, it is positive, so the force must be along minus r cap. If both are negative, then Q1, Q2 positive, force must be along minus r cap. If Q1, Q2 are of opposite sign, then this encircled term will be, this term will be negative. So the force has to be in this way. So along the r cap. That's why we have kept minus r cap, minus minus here plus, and it will become along the r cap. This is the need of keeping this minus r. Now you remember this force we have written, force experienced by 1 due to 2. And this is equal and opposite of force experienced by 2 due to 1. Means this force F12, force experienced by 1 due to 2, and force experienced by 2 due to 1, they are equal and opposite. Now here only one note I want to write. Whenever use vector equations, substitute charges with sign, right? So once again I'll say, when two charges are placed in the space with position vector r1, r2 in vector form, force experienced by 1 due to 2 will be this one. Vector equations generally we use in those cases where we don't have, in three-dimensional cases, it is no doubt is going to be the best way to use the vector equation, because we won't be able to visualize the things in three-dimensional space. Now some basic factual points about the Coulomb's law. You say this Coulomb's law is an action-reaction pair. Means within the classical physics domain, F12 and F21 are forming the action-reaction pair. Now there is a significance of the word within the classical physics domain, because in the relativistic physics these two forces don't come at the same time. Later on in the advanced video we'll discuss this point, here not required. So it is an action-reaction pair. It acts along the line joining the charges. 2 point charges are there. The force will be this. Force will be, if 2 point charges are like this, then this is along the line joining the charges. This is what I'm trying to say. Then it depends on the medium. Means like the gravitational force does not depend on the medium, that whatever is the medium, the gravitational force is going to have the same expression, but this particular value, this particular force depends on the medium. In vacuum it is having one value, in water it will have another value. So when the two charged particles are placed in some other medium, the force is going to change, and we'll discuss this particular point later on also when some medium has been filled. Here if you see this particular expression what we have written, this is only when the two charges are placed in vacuum. If some medium will be here, then it will be changed. How it is going to change, we are going to discuss it further. Now it is a long range force. Long range force means it depends, it is valid for heavenly separation. If the two charged particles are placed at say 10 to the power 15 meter of distance, for that distance also this expression is valid. And if they are placed at a separation of 1 micrometer, then also this is valid. So it is a long range force. It is central force. It is conservative force. Work done by the electric force is independent of the path. Along a closed path is going to be 0. It is valid only for point charges. You remember this particular expression, F equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square, you can apply only for the point charges. If you have to find the force between two extended charge particles, then you have to go for the integration technique. Few questions will discuss how to use the integration technique, right? So it is valid only for point charges. Remember, if extended objects are there, then we cannot use this expression directly q1 q2. Like if I say, somebody say this is 1 meter rod, some charge q1 is there, and this is another point charge q2, and this separation is half meter or 1 meter, then here you cannot use F equal to K Q1 Q2 upon R square. What the separation you will write? Will you write the separation as half meter, or you will write the separation as 1 meter, or you will write the separation as 1.5 meter? So we cannot use this particular expression F equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square for this type of extended object. So here we have left only with one solution, that we have to go for the integration technique. And remember, don't try to replace the extended object charge by a point charge placed at its center of mass. That is going to be a wrong concept, valid only for point charges. It is an example of action at a distance. Meaning of the word action of a distance: when the 2 point charges are placed at some separation, then also they are going to attract each other. Means this is not a particle, the force between two charges or two particles when they are on contact only. Even when there are some separation, then also they attract or repel each other. So these type of forces we call the example of action at a distance. And the most important point, it is a two particle interaction. What is the meaning of this two particle interaction? Let us say if two charges are there, Q1 and Q2, and they are exerting a force on each other. Say they are exerting a force F on each other. This Q1 and Q2 are there, they exert a force F on each other. Say I am saying attractive force. Now this force, if some other point charge also comes Q3, then this force F experienced by Q1 due to Q2 won't change because of its presence. This remains, please observe the lead. The force experienced by Q1 remains same as earlier, whether this Q3 is present or not. Presence or absence of Q3 is not affecting the bonding of Q1 and Q2. Presence of Q3 or any other charge is not affecting the bonding of Q1, Q2. So this is a two particle interaction. The force between Q1 and Q2 is independent of the presence or absence of any other charge. The force between two charges is independent of the presence or absence of any other charge. Very, very important point. Force between two charges is independent of the presence or absence of any other charge. Here another important point comes, and that is this statement is valid only for point charges, because when we have the extended object, then this statement is having some exceptions. when we are having the extended object, then the presence of one may affect the force between those two other objects because of the electrostatic induction. So this statement, I say, is valid only for the point charges. Right? Now, come to the next part, principle of superposition. What principle of superposition is saying? As you already know, principle of superposition is saying means the force experienced by one charge particle due to many charge particle when you have to find. Then this principle of superposition is telling that force by one charge due to a number of charges is given by vector sum of forces experienced by considered charges. Means let us say you are having 5-6 charges, say q1, q2, q3, q4, q1, q2, q3, q4, 4 charges, and here you have q0. You want to find the force experienced by q0. Force experienced by q0 you want to find due to these all charges together. Now we know the force experienced by any charge or electric force is a two-body interaction. So force experienced by q0 due to q1 is, say, F1. Force experienced by q1 due to q0 due to q1 is q0. And say force experienced by q0 due to q2 is this one. Force experienced by q3 due to q0 is this one. And force experienced by q0 due to q4 is this one. Say this is F2, F3, F4. Then what is the total force experienced by it? Vector sum of F1, F2, F3, F4. This is only the principle of superposition. If you have to find the force experienced by one charge due to remaining charges, multiple charges, find out the force experienced by considered charge. Find out the force experienced by considered charge, this charge, due to individual charges. Due to this charge, due to this charge, due to this charge, due to this charge. And then add them all vectorially. You have to remember only this, that force is a vector quantity, so you have to add them vectorially. You see it is there written. Q1, Q2, Qn, say n charges are there. Here Q0, you want to find the force experienced by this one. So it will be force experienced by Q0 due to first charge, due to second charge, due to third charge, and so on. So total force experienced by F0 will be this vector sum. And when you solve, it will come like this. There's no need of remembering it. Only expression you remember is 1 upon 4 pi epsilon naught q1 q2 upon r square, or in the vector form you can remember. Now how come this principle of superposition holds good? This is possible only because of this statement. Force between two charges is independent of the presence or absence of other charges. Only because of this statement we are able to apply the principle of superposition. Now we are discussing one next point which is going to be very important, which I already telling you. What happens when the when some medium is there between the 2 point charges? Try to understand this point, because already JEE Main has been asked a question, very conceptual question on this, and the advanced people have also asked. Even though the key of those two are not matching, later on in the question part I'll mention that also, but I want to tell you this, what is the actual concept here. So first you see what is the myth about this particular point in the people mind. If 2 point charges are there, q1, q2, placed at a distance r, in vacuum, then we say they attract or repel each other with a force which is equal to 1 upon 4 pi epsilon naught q1 q2 upon r square. And if some medium is there, in some medium, the force between the charges, force between the charges, that is force experienced by one charge particle due to other, it is equal to 1 upon 4 by epsilon naught epsilon r q1 q2 upon r square, where epsilon r is the relative permittivity of medium. It is also known as dielectric constant, and this epsilon naught epsilon r we denote by epsilon. It is the permittivity of the medium. So these are the simple things. What is the flaw here? People say this F in some medium, the F is the force between two charge, force experienced by Q1 due to Q2. But if I say this, then it is violating that statement that force between two charges is independent of the presence or absence of other charges. Then in this medium, the force changes. So this particular thing creates the trouble. And what is the core reason? What is the wrong? Actually here, this statement itself is wrong to say that force between two charges. We have to say rather, here the correct statement, I am marking it in red, it is wrong statement, right? Correct statement will be resultant force experienced by Q1 or Q2 due to other in the presence of some medium. This force F, this F is not the force between the two charges. It is the resultant force experienced by Q1 or Q2 due to other charge in the presence of some medium. Now, this particular thing I am trying to explain in detail. You see, we have two charges, Q1 and Q2. One Q1, Q2, which are placed at a distance of r. This separation is r. And here we have some medium. This is a medium is filled. Due to these two charges, some disturbance will arise in the medium. Redistribution of charge will take place. So here in the medium, this negative charge is on the left side, positive charge is on the right side. This type of thing appear. Now Q1 will experience the force due to Q2 as well as due to these induced charges, these charges which appear at the surfaces. This phenomena is known as polarization. This phenomena is known as polarization. Later on, we'll discuss this particular point in detail in the capacitor chapter. But this phenomena is known as polarization. Because of the presence of one charge, something is happening in this. What is that something happening? Some redistribution of charges happens, and that thing is known as the polarization. Now, that polarization is happening, so those induced charges, polarized charges, are also exerting the force on Q1 or Q2. So see, the net force experienced by Q1 is one is due to Q2 and other is due to the polarized charges, right? Other is due to the polarized charges. Now, this total resultant force is equal to 1 upon 4 pi epsilon naught epsilon r q1 q2 upon r square. And force due to Q1, force due to Q2 is not changing. It remains same. So if I say total force total force is 1 upon 4 pi epsilon naught epsilon r q1 q2 upon r square, and force by 1 due to 2 q1 q2 upon r square, and force experienced by 1 due to induced charges. This term we say with some misconception that this is equal to force experienced by 1 due to 2, but actually this is the force experienced by 1 due to 2. This is the total force experienced by 1 due to 2 in the presence of the medium. So here a very important statement you can say: force experienced by q1 due to q2 is not changing because of medium. Rather, the resultant force experienced by q1 due to q2 or vice versa is given by this. So this particular expression is not force by 1 due to 2. It is the total force experienced by q1 due to q2, which is including the force experienced by q1 due to q2 plus the force experienced by q1 due to the polarized charges of the medium